Morning, everyone. My name is Joshua. I'm a tech lead at SambaNova, and I work primarily on our front-end integration with ML frameworks like PyTorch and hopefully soon stable HLO. Today, I'm going to be talking about the details of a technique we're using to integrate C++ programs with incompatible dependencies. Specifically, we use this in an integration between SambaNova and Node.ai's compilers. Before I get into the details of that, I want to give a quick primer on SambaNova for those of you guys who haven't heard about us. So SambaNova is a systems company. We make ML chips called the RDU, which stands for Reconfigurable Data Flow Unit. So our chip has a data flow architecture, and we have an integrated software and hardware stack for running on this chip. We actually just announced our most recent chip last month, and it has stats that are in the similar ballpark to say, the H100. So we're targeting data center inference and training workflows. Okay, so about the problem at hand. So the context here was that we wanted to have a collaboration between SambaNova and Node.ai, where we would take the front-end part of the Node.ai compiler and plug it into the back end of the SambaNova compiler. And from the onset, we thought this would be a pretty easy integration because both of the companies have MLIR-based compilers. However, we quickly ran into problems because Node.ai is using LLVM head and SambaNova is using LLVM 12. And if any of you guys have worked with multiple versions of LLVM, you know that LLVM does not care about backwards compatibility for their internal APIs, and it can be a massive amount of work to switch between them. This was a project with a short timeline, so we definitely did not have the ability to change the version of SambaNova's LLVM or Node's version of LLVM to be compatible. So we needed to find another way forward. So yeah, this is about how we found a bridge to get the two compilers to work. So basically two classes of solutions we considered for this project. The first one that seems pretty obvious is a common serialization format. So you don't bring the two compilers directly together. You have one dump out all the state to disk, and then the next compiler reads it in and does its thing. Since we have MLIR-based compilers, an MLIR bytecode serialization format seemed natural, but it turns out to deserialize an MLIR or serialize an MLIR bytecode, you need to be able to represent the dialect that the bytecode is in. And Node's dialect was incompatible with SambaNova's LLVM version, and SambaNova's dialect was incompatible with Node's LLVM version. So we could not directly use the MLIR bytecode. So we would have needed to do something else. We need to find a common serialization format. So we could have created something custom. But again, we were on a short timeline, so that did not seem viable. And stable HLO would actually be a great middle ground, right? This is an MLIR dialect that's designed to be stable, usable with multiple versions of LLVM. But neither of us were super familiar with it at the time, and so we decided, given the short timeline, to explore other options. So the second category of integration solutions we were looking at was basically, can we expose the existing C++ API on the SambaNova stack for creating our IR, right? So there's an API, already exists. You can use it. If Node's compiler could just directly call the API, life would be great. So, one way you could do this would be gRPC or like a WebSocket-based communication, but then you do have to, bring in such a server and client and wrap the API in the appropriate protocols. So that did seem like significant work. And so the ideal situation would be really just directly call the API from have Node's compiler directly call the SambaNova APIs. But obviously this can't work because they have different versions of LLVM. But what if we could do that? There's only a few problems. Compiler doesn't like this. The linker doesn't like this. Runtime doesn't like this. The whole computer is out against us. But The good news is we were actually able to get this to work. There are solutions at each of these levels. And so the rest of this presentation, I'm going to sort of walk through a toy example of the issue we faced and how the problems manifested at each of these layers and how we were able to solve them. So let's get into that. So here is an example problem that sort of represents what we were doing. We have two XKCD style random number generators, one that returns 6, one returns 16. These stand in for the two versions of LLVM. It's called the 6 RNG LLVM 12 and the 16 RNG LLVM head. And our goal here is we want to have a main program that can use both of them together. So if you do the naive thing and in your main program try and include both headers, anyone in CS 101 will know this will go very poorly. You get a compiler error. C++ has the one definition rule, which says a given symbol can have one definition, hence the name. And so, yeah, we're trying to include two definitions. Compiler says, no, that's not allowed. Obviously, LLVM, you've got two versions. They have symbols of the same name, same implementation. You will run into this immediately if you try and directly include the SambaNova headers and the nod headers in the same file. So this problem, at least, can be worked around in a relatively straightforward fashion. The trick to get the compiler to accept your code is you make sure the compiler only sees one definition at a time. So you can do this. Here I introduced this RNG2 class, which wraps one of the versions of our random number generator behind an opaque pointer. So if you see here in the main function, we're now including the header 1, the original version of the random number generator, and we're not directly including header 2. We're instead including this hide header 2 file. And hide header 2 then has RNG2 class with an opaque pointer in it, and in the CPP file, that's where the actual header 2 gets imported. So when you compile a hide header 2 translation unit, you only see header 2. When you compile a main translation unit, you only see header 1. The compiler does not see a one definition rule violation, and you should be good until you run it. So now the compiler is solved, but we run into issues with the linker. So C++'s one definition rule does not apply per translation unit. It applies to the entire program. But if you violate it in the entire program, then it's not going to be violated. The compiler isn't the one that catches it. It's the linker. And the spec says the linker does not have to report this error. It's undefined behavior, and it can do whatever it wants. So in practice, if the linker sees two definitions of the same symbol, it picks one and throws out the other one because it assumes they're the same. So that's what happened here. Our header 1 version is thrown out. And when we compile this whole thing, we see random number 1 and random number 2 are both 16. We did not get both of our versions of the random number generator into our program. So how do we get around this? Well, the solution here is we need to hide the two versions from the linker. And the way you do that is you make sure that you compile them into separate binaries, separate elf binaries.so files, and you make sure that they're not linked. When you're compiling these guys, or I guess when you're linking them, you don't tell the linker about the other one. Instead, you link the two binaries at runtime using dlopen. So this is what the dlopen procedure would look like. We compile header 2 into libhideheader.so, dlopen it, extract the symbols, and call that. And dlopen requires you to give the symbol name. So for things to be reliable, you actually need to use a C API, which is what I had on this slide, using some extern C stuff. So that way, dlopen proceeds without issue. So now we have the two versions of our random number generator, standing in for the two versions of LLVM, compiled and linked in separate ELF binaries that are not connected to each other at all statically. And it's only at runtime, once you actually enter the main function, that the two get brought together. And so this actually does work. If you look at the output here, we do have random number 1, 6, random number 2, 16. That's pretty exciting. Unfortunately, we've done a simplification here. So the simplification we did here is we only have two ELF binaries. We've got our main a.out and this libhideheader.so, and the conflicting symbols were statically compiled into our two main binaries, right? So the RNG in both guys has static linkage. They're not dynamic symbols. If you look at the actual compilers, you don't statically compile LLVM into your compiler. You compile it to a .so and dynamically link against it. So instead of two binaries at play, we have four. The nod compiler dynamically links to the LLVM head. The SN compiler dynamically links to the LLVM 12. So if we adjust our example to look like this as well, basically we pull our two versions of the random number generator, header1 into libheader1, header2 into libheader2, make some code changes here so that there's CPP files for them, compile them, and all of a sudden it's no longer working. Now we're seeing 6 for both cases instead of 6 and 16. So we've now solved the linker issue, but we've encountered the runtime problem. So what's going on here? The basic idea here is that ldlinux.so, the dynamic linker, has a cache in it mapping symbol name to implementation. And so when you first load our main binary, it has in the ELF dynamic section, it says, hey, I need libheader1 and the RNG symbols. And so before we enter the main function, the dynamic linker gets invoked. ldlinux finds libheader1, brings it into the process, finds the RNG symbols inside libheader1, adds it to its cache, resolves the references in our main binary to the RNG symbols to these guys in libheader1. Now we go into the main function, and the main function we call dlopen. dlopen then loads libhideheader.so. As part of loading this guy, dlopen says, hey, there's a dynamic section. I got to call into ldlinux, the dynamic linker, to resolve the things in the dynamic section. So now in libhideheader, ldlinux says, okay, I see I need libheader2, finds it, loads into the process without issue, and then says, okay, I need these various RNG symbols, and says, oh, I already know where those RNG symbols are. They're in header 1. Maps them in, and you get the issue we saw. Random number 1, 6, random number 2, 6. Both symbols were resolved to the same place. And fundamentally, the issue here, or design decision here, is that the ELF dynamic section lists symbols you need and dynamic libraries you need, but it doesn't say which dynamic library a given symbol should come from. So from the linker's perspective, when it's loading libhideheader2, it said, the thing said, I need libheader2.so. Dynamic linker found that and it said, I need an implementation of this RNG symbol. And dynamic linker found that. And dynamic linker, the ELF spec doesn't say RNG symbols should come from libheader2. They just say, I need an implementation of the RNG symbols. And so the dynamic linker resolves this happily with the file, with the implementation we don't want. So what's the solution for this? ELF symbol versions. So ELF symbol versions were developed by glibc as a way to have multiple implementations of a given symbol so that they could maintain backwards compatibility with the C standard library. They put out a new version of the backwards incompatibility change. The new version has the new implementation has a different version on it than the old one, and that way when you load a program, that program says which version it needs and they can coexist. And in fact, that's exactly what we need here. We need two versions of the same symbol to happily coexist. So you use a version script that looks like these guys. Syntax is where it says header 1 before the open brace. That's the version string that gets put into the binary. And then inside the brace block where it says global : star, that's identifying which symbols this version should be applied to. Star means apply it to everything. So when you compile this, you use the version script pointed to the .map, compile them, run, and it worked. This is what we're going for. We now have random number 1, 6, random number 2, 16, and all the pieces fit together. When the linker went to resolve the RNG symbols in libhideheader2, it doesn't say I need the RNG symbol, it says, I need the RNG symbol of version header 2. And so then the linker found the correct symbol. So yeah, that's what I wanted to share with you guys. This is the technique we're using to combine two C++ programs into a single process with incompatible dependencies. And I know like OpenXLA is all about integrating different projects. So I imagine a lot of you will probably run into this at some point or other. So hopefully this is a helpful little explanation and presentation for you guys you can take back. Again, in summary, the trick we used here was we used a C API with opaque pointers to hide things from the compiler, to hide the multiple implementations from the compiler and linker. And then we used ELF versions to let them coexist at runtime. And in my experience, figuring out how to do the C API stuff is pretty straightforward, and finding information about ELF symbol versions is miserable. So hopefully this will save you guys a lot of time if you ever run into this situation. Going forward in SambaNova, we're pretty excited. We've worked out all the details for this and have successfully integrated conflicting projects like that, and are looking forward to integrating with more projects without worrying about dependencies lining up. So stable HLO is our next target. We really want to plug into PJRT and stable HLO and get that working with the SambaNova stack. Yeah, we also want to engage more with the open source community, so expect to see us on the mailing list talking about these integrations going forward. Quick shout out of thanks. A whole bunch of people helped out with this on both the SambaNova side and not AI side with this engagement and working out the details of the linking. So thanks to everyone here. Any questions?
So I'm curious, how many APIs do you actually have to support in this way? Like, what's the surface like?
Yeah,
so this was an example of a simple function call, right?
Mm-hmm.
And it required like multiple steps to kind of plan everything through, right? Does it scale with the number of APIs that you need to support?
Yeah, so the most important part about this is basically if you need to compile your code and all of your dependencies that you're vendoring with a unique symbol version. And this means when they get loaded into a big process address space, like say Python, or something like this where you're being more intentional, your dependencies are going to be isolated and no one else will wreck your system. Then so the C API, for everything that you want to expose over the interface, you do need to expose to this extern C. It tends to, at least in our experience, there tends to be a fairly limited surface of API calls you actually need to invoke to get across. And it's not terribly hard to code gen a C API from a C++ API. This is something we actually ended up doing in practice. So we found it does tend to scale at least to on the order of like a couple thousand functions.
So did you use some sort of clang tooling to basically emit these C APIs based on your C++, or how did you go about it?
I had a Python script which parsed the abstract syntax tree of the headers we cared about, and then had some heuristics for turning them from C++ into C. So basically had like a type map kind of thing. And that was all that tended to be needed.
I'm curious if you have any ideas, like, say you were in charge of all these libraries, and like, if you could, what would this ideally look like for you? Like, you sort of had to do all these steps given what you had control over, but like if you controlled LLVM or whatever other libraries you had to integrate with, is there anything that could make your life easier? Or is this actually like a pretty good outcome?
Yeah, that's a good question. So I think if you really want to be able to call directly from one process, from one C++ program to another in the same process space, I think this is pretty much the end-all be-all of that. What would make your life easier is putting them in separate processes and using like a gRPC, and then you don't have to worry about these at all. Within a process, really good backwards compatibility also solves this issue, right? The fundamental reason why we ran into this with the LLVM dependency is the two versions of LLVM had symbols with the same name and the same version and different implementations. And so then the linking gets confused. But if like it was something like glibc, you don't run this into this with glibc because glibc is very careful about backwards compatibility. And when they introduced, so they managed symbol versions on their side in a coarse-grained fashion. So they, or in a fine-grained fashion. Every function in glibc has its own version. And when they make a backwards incompatible change, they keep the old one and have the new one with a new version. And so this means you can load the newest glibc and all your programs back into history will link successfully to it, at least in theory. So in our case, right, if LLVM also maintained similar backwards compatibilities from an ABI perspective, that would make this a lot easier. But,
yeah, that makes sense. Thank you.
Hi, first, thanks for sharing your adventure. I feel like I felt all your pains as you went through that. I just want to say Stable HLO feels like a great fit for this. This is kind of the use case we were pretty much made for. About a year ago, I presented about Jack's native serialization, which was the producer was on one version of LLVM and then the consumer running on a server elsewhere was on a slightly different version of LLVM. So it's something we've actually showed works in production. But my question was more on, is there any intention of bumping your LLVM version just because Stable HLO does use MLIR bytecode format for maintaining its compatibility guarantees?
so yes, on a long-term horizon, but no on a short-term horizon. So I know we've got some folks from Google who talk about how Google has a dedicated team whose entire job is merging LLVM 12 twice a day. And as a startup with of 100 engineers, right, we don't have the manpower to do something like that. And so the current policy is we're going to upgrade our LLVM when there's a good business case for the new version, which likely means post IPO. And at least from my perspective, we'll see. We'll see how the situation develops, right? If there's a new version of LLVM that has a feature that unlocks business opportunities, then there's a reason to invest in this. But as of right now, we have sort of chugs along successfully, and so I think for the short to medium term, I don't think we see an LLVM upgrade in our future.
Yeah, we'll follow up after. Can think of alternate things too.